Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on February 9th, 2026, about 5 days ago. It introduces a feed-forward framework that tackles the difficult challenge of monocular 4D reconstruction, delivering a nearly 40% improvement in geometry reconstruction and a 25% boost in motion estimation compared to prior work. The paper is titled MotionCrafter, Dense Geometry and Motion Reconstruction with a 4D versus AE. And as we'll see later, the implications for how we align latent spaces in diffusion models are quite significant. For those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the overall pipeline. On the left, the system takes a simple monocular video, like this breakdancing sequence, as input. The middle panel shows how the model lifts these frames into a shared world coordinate system, which allows it to reconstruct the full 4D sequence coherently. Finally, on the right, it simultaneously outputs dense scene flow estimation and a dynamic point cloud, achieving this without the slow test time optimization typical of prior work. Figure 2 lays out the MotionCrafter architecture. At its core is a novel 4D versus AE, shown in the bottom right inset, which encodes geometry and motion into a unified latent space using separate encoders. In the main pipeline across the top, a Diffusion UNet processes this 4D latent to generate the final reconstruction. Crucially, as seen on the bottom left, the model conditions this process on video latents from a pre-trained, stable video diffusion model. By not forcing the 4D latents to strictly align with the video distribution, the system achieves better generalization. Figure 4 illustrates why these design choices matter by comparing different normalization strategies. The top row depicts a close-range scene, while the bottom row challenges the model with a large-scale outdoor environment. On the far left, using the original versus AE with standard max rescaling results in total failure for the outdoor scene, producing mostly noise. The middle column shows that fine-tuning just the decoder improves things slightly, but the geometry remains blurry. In contrast, the right column confirms that fine-tuning the entire versus AE with the authors mean normalization strategy successfully recovers clear, detailed structures. Well, having validated the normalization strategy, Table 1 presents the main quantitative comparison for joint geometry and motion reconstruction. The top section focuses on geometry, where MotionCrafter, in the last row of the block, consistently achieves the lowest relative errors on datasets like Spring and VKitty2. The lower section reports motion estimation metrics, such as endpoint error. Here too, the method secures the top spot with an average rank of 1.0, significantly outperforming baselines like 0MSF and Pomato. While the previous results covered the joint task, Table 2 specifically evaluates world-centric geometric reconstruction. The comparison is split between camera-centric baselines at the top and world-centric approaches below. MotionCrafter, in the final row, outperforms all others on the Monka dataset with a relative error of roughly 26%. It achieves this with a competitive average rank of 2.67, notably avoiding the slow post-optimization used by top competitors like Geo4D. So while the previous table showed the final performance, Table 3 breaks down the internal design choices for the geometry versus AE. The first section evaluates the versus AE in isolation. Notice the massive gap between the first row, VAE1, and the fourth row, VAE4. Switching from the original max rescaling to the proposed mean rescaling with full fine-tuning slashes the relative error on Cintel from nearly 40 down to about 5.7. The bottom section confirms that these gains hold up during generation, with UNet 2 consistently outperforming UNet 1. Alright, having confirmed the design choices, Figure 9 provides a visual comparison against state-of-the-art methods like 0MSF and Delta. The columns from left to right display the ground truth, MotionCrafter, and the competing baselines. In the first row, the model matches the scene flow accuracy of 0MSF, even though it wasn't trained on that specific dataset. As we move to the other examples below, MotionCrafter clearly outperforms the others, preserving sharp geometric structures where the baselines tend to produce noisy or incomplete results. Wrapping up, MotionCrafter stands out by delivering robust 4D reconstruction in a feed-forward manner, effectively eliminating the need for slow per-scene optimization. More broadly, it challenges the standard assumption that geometric latents must strictly align with RGB distributions, proving that a relaxed normalization strategy actually yields superior details. This insight could fundamentally reshape how future geometric diffusion models are designed. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.